Hey everyone, and welcome back to ByHollyG. Welcome to today's video. I have been really excited to sit down and film this video with you guys because, as you may know, I ran the London Marathon this year. I'm wearing my marathon jacket, and in this video I'm basically going to be drawing parallels between my experience and the biology behind running a marathon and preparing for a race. Obviously I'm not going to cover everything, but I'm gonna dive into a bit of the biology behind running, and in particular running a marathon, which is a very long endurance event. So I hope you enjoy this video. Give it a thumbs up if you do, comment down below if you have any questions or video ideas, and definitely subscribe if you want to stick around for more biology content on ByHollyG. So the first section of this video is going to be all about my preparation for the race, and in particular my taper week. So a taper week is when your training intensity subsides gradually. I unfortunately came down with an injury, an Achilles injury, so that meant my training basically came to a halt. I didn't do much running at all in my taper week, but looking back on it, it may have been a blessing in disguise because, you know, in me not running, my body could fully recover from all of the training which had been so intense, reserve the energy, and I was basically carb loading in that taper week, which is what I'm going to talk about first. Like, what is carb loading? And we're also going to address what is glycogen. So carbohydrate loading, or more commonly referred to as carb loading, aims to increase the amount of glycogen stored in your body above normal amounts. So we can say that it is super compensation. Carb loading means specifically focusing on carbohydrates, getting the majority of your energy from carbohydrates as opposed to the other macronutrients being fats and protein. Glycogen is essentially an energy storage molecule in the body, and we find it in two places predominantly. So the first being your muscle cells, otherwise known as muscle fibers, and the liver. However, the liver only stores about 20% of total glycogen. It is essentially what we call a polysaccharide. Now, polysaccharide, if we break that down, it means many sugars, because saccharide means sugar and poly means many. So glycogen is many sugars. It is many monosaccharides joined together, and that monosaccharide unit is glucose, specifically a form of glucose that we call alpha glucose. But many glucose molecules are joined together by glycosidic bonds to form this insoluble glycogen energy storage molecule. So I'm just going to specifically talk about muscle cells, because what happens is when we consume food and glucose is absorbed from the digestive system into the bloodstream, it will circulate throughout the body in the blood, and it's taken into muscle cells specifically through a glucose transporter molecule that we call GLUT4. So that's almost like a gate that allows glucose into cells, and we increase the number of those gates or those transporter molecules in the membranes of those muscle cells in response to insulin and muscle contraction. So when glucose levels rise in the blood, that means we release more insulin, and insulin allows more glucose into cells by increasing the number of these GLUT4 transporter molecules in the cell surface membrane of those muscle cells. As I said, when your muscles start to contract, that also means we demand more glucose, and that also results in more of these GLUT4 transporter molecules being put in the cell membrane. And so once glucose is then inside the muscle cell, it will be phosphorylated. And what we mean by that is we add a phosphate group, so a PI, which stands for inorganic phosphate, to glucose. So it becomes what we call glucose 6 phosphate, and that traps it inside the cell, so it can't now escape. From there, this glucose 6-phosphate can either be channeled down a metabolic pathway that we call glycolysis. Now, I recently made a video all about glycolysis and the mechanism of glycolysis, so you can check that out if you're interested, and that would normally be funneled through the aerobic respiratory pathway, which results in the production of energy. And in our bodies, we want to generate energy in the form of ATP. Or on the other hand, that glucose 6-phosphate can be channeled into making glycogen, which is what we're talking about, you know? And that is favored when we're resting, because when we're resting, our muscle cells aren't demanding energy, i.e. ATP. So we're gonna channel that glucose 6-phosphate into making glycogen in a process that we call glycogenesis. Genesis meaning to make something, so glycogenesis making glycogen. So now let's talk about carb loading. You know, as I said, the aim of carb loading is to increase the amount of glycogen stored in our bodies above normal amounts. So we're super compensating with glycogen. So the way in which this is achieved is, as I said, by increasing your carbohydrate intake and decreasing the amount of exercise you do. So as one increases, the other decreases, and that is what you do during your taper week. Originally, the way in which this glycogen super compensation or this carb loading was achieved was through basically making someone do a lot of strenuous exercise so that their glycogen stores were depleted, and that was then followed by 2 to 3 days of eating a carbohydrate poor diet, so one that is rich in fats and protein, and then after that they would then consume a carbohydrate rich diet, so one that is focused on carbs, not so much protein and fats, and that achieved glycogen supercompensation. But as I said, the first strategy that I mentioned, so by increasing your carb intake and decreasing the amount of exercise you do, that can achieve the same level of glycogen supercompensation, but it just doesn't involve that first period of really intense activity followed by this high fat, high protein diet and then the carb rich diet. So the next part of this video is going to talk about energy metabolism during the race. So where do we get the majority of the energy from so that we can run for those 26.2 miles, you know? I essentially woke up on that day, I was really quite nervous. I actually woke up shaking because I was so nervous, but I was also cold at the same time. But as I said in my official marathon video on my main channel, I had so much energy on the day and I was running at a pace a lot faster than I'd planned. I think it was a combination of the fact that, you know, I'd carb loaded quite a lot, so my muscles were filled with glycogen and I had so much energy for the race, and then I also had this huge adrenaline rush because I was so excited, a bit nervous. So we're going to talk about the use of glycogen during the race. We're also going to touch on fats, and we're going to talk about adrenaline as well because it does play a big role in these like races when you're under a bit of pressure and you're worried. So the first thing to say is that during endurance events, the main two sources of energy, or otherwise ATP, come from intramuscular glycogen, so the glycogen stored in your muscle cells, and intramuscular triglycerides. Triglycerides, they are a form of lipids, and you can think of lipids as fat, and they're composed of a single glycerol molecule joined to 3 fatty acids. That is a triglyceride, and we also store those as like these droplets in our muscle cells alongside the glycogen. When we exercise basically at a moderate to high intensity, our body primarily uses this glycogen, this intramuscular glycogen, and we know it is so important because the more glycogen someone is able to store in their muscles, the better they're able to perform, or the longer they're able to run for. However, from studies, we know that this intramuscular glycogen only really provides enough energy for running at a moderate to high intensity that lasts about 2 hours. So during a race, when you're running the marathon, your glycogen levels will be being depleted, and before they're entirely depleted, you will start to feel the effects probably, and when they are entirely depleted, you will struggle to run at quite a high intensity anymore. You will be forced to reduce your pace. We know that you probably won't be able to sustain a power above 70% VO2 max. So VO2 max can be used to measure power, and it measures specifically the maximum amount of oxygen consumed during exercise. Obviously that doesn't really account for like fueling on the run and stuff, which we are going to touch upon, but we're just assuming that glycogen stores are depleting as you're running and you're not replenishing those energy stores. So glycogen, as I said, is our first primary energy source. But I just want to touch upon, you know, liver glycogen and the glucose that's circulating in our bloodstream. Why don't we use that for exercise instead of that stored in our muscles? There are a few reasons for this. You know, the first is that intramuscular glycogen, as opposed to say glycogen stored in the liver, doesn't need to be transported anywhere. It's at the site of muscle contraction, so it's therefore more efficient to use muscle glycogen as opposed to liver glycogen. And that circulating glucose instead is used to provide energy for essential bodily processes like brain function that obviously have to keep going as we're running, and it only represents about 5% of the total energy we could get from glycogen in our muscles, that circulating glucose. So that is used, as I said, for other processes like brain function. And liver glycogen on top of that has a really important role in maintaining blood sugar levels so that they don't like rapidly decline. Another point to make is that we also yield more energy from glycogen than glucose itself. Even though glycogen has to be broken down into glucose to then be used to generate ATP, it is more efficient in that sense because we generate more energy per gram of glycogen than per gram of glucose. So we're now going to talk about those triglycerides, those intramuscular triglycerides, but it's important to compare carbohydrates and triglycerides or fats as energy sources. Carbohydrates can be metabolized really efficiently. They can be metabolized with oxygen and without oxygen, and they provide energy really rapidly, whilst fats, on the other hand, they can only be used to generate ATP when we have oxygen available, and they take a lot longer to generate that energy, so it's not as instant an energy source. Fat metabolism also requires derivatives from carbohydrates, so the metabolism of fats almost relies on that of carbohydrates, but fats do have their advantages. In comparison to carbohydrates, fats can be stored without water. We need a lot more water to store carbohydrates as opposed to fats. They provide energy, although slower, over a longer period. As I said, glycogen runs out after about 2 hours, whereas fats can provide energy for low to moderate exercise intensity for a longer period. Even though these fat stores do provide, you know, as much energy, if not more energy than the carbohydrate stores, we only really see these intramuscular triglyceride stores being used when carbohydrates are limiting. As I said, when your glycogen stores start to be depleted, you will start tapping into your fat stores, those intramuscular triglycerides, and you'll obviously have to reduce your intensity at that point as well to ensure you have oxygen available to metabolize the fats. Studies that have looked at like fat loading as opposed to carb loading are really quite interesting, because even though it seems to increase the amount of intramuscular triglyceride that is stored in your body, it causes a depreciation in performance, in athletic performance, especially in these endurance events. And that's despite the fact, as I said, we're increasing the amount of intramuscular triglyceride. We think the reason for this is because with a high-fat diet, one that is focused on fats, you compromise the ability of your muscles to store intramuscular glycogen. And as I said, that's our primary energy source during these endurance events. The final thing I want to say before we look at adrenaline is that as you train and you become fitter, you firstly are able to store more glycogen in your muscles. And secondly, what your body will start to do as well is it will adapt to using more of those fat sources. So it will derive a higher proportion of energy from fats over glycogen, and that is really advantageous for our bodies, because if you are able to tap into more of those fat sources, you can preserve more of your glycogen, and it will mean that you don't hit the wall as soon, and you can also reserve more of that glycogen and that carbohydrate as energy for other functions like brain function, because our brain primarily relies on glucose. This next section is all about adrenaline. Everyone has heard of adrenaline. It's also called epinephrine, and it's a hormone in the body that causes a range of effects. Adrenaline is basically released from our adrenal glands. They sit just above our kidneys, and adrenaline is an amine hormone. It's derived from an amino acid, the amino acid specifically being tyrosine. But adrenaline, it causes this fight or flight response. It basically is released upon stress, whether we're stressed physically or we're stressed psychologically. Adrenaline will be released, and it basically prepares our body for like strenuous exercise. So it is really beneficial during these races, and we're going to just talk through some of the effects of adrenaline and how that helps with running. The first effect is that it increases your heart rate, and it also increases the force of cardiac muscle contractions. So together with an increased heart rate and more forceful contractions, more blood can be pumped around the body to not only your muscles but also your brain cells. It also causes what we call vasodilation, which also helps to increase blood flow. As well as causing changes to our blood flow and our heart, it also causes dilation of our airways, so we can, you know, inhale more oxygen and breathe out more carbon dioxide as waste from respiration. I will talk about sweat a bit more later, but obviously when we're running, we're going to be sweating and we're losing fluid through sweat. And what adrenaline does is it limits the amount of fluid lost in urine. It also stimulates the breakdown of glycogen in both the muscle and liver cells. So that is what we call glycogenolysis, so that we can have more glucose for respiration and ATP or energy generation. The last thing I'll say here is that adrenaline is really clever in that it limits the amount of glucose that is taken up by non-working muscle cells in our body, for example those of the digestive system. So it therefore prioritizes glucose uptake in the working muscles that are needed to keep us running. I have mentioned this, but I just want to go into a bit more detail about hitting the wall. It's kind of described as this state of being so exhausted physically and mentally, and I think I hit the wall at around 20 to 21 miles in. It was the point when Emily and her boyfriend Dan were shouting at me, being like, Holly! 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 5 miles! And I was literally like, 5 miles is still a really long way. And at that point, all I was thinking about was getting to the finish line and just putting one foot in front of the other. I could not think about anything else. I couldn't even vlog at that point very well because I was just so drained. As we've already talked about, for the first 2 hours you're relying mostly on that intramuscular glycogen, and if you didn't eat anything during the race, then you would reach a point when all of your glycogen in your muscle is depleted. You would have to switch to using intramuscular triglyceride and other fat sources, because obviously we do store fat in adipose tissue and other parts of the body. However, to metabolize fats, as I said, you have to have oxygen and you have to be running at a lower intensity, so you would be forced to slow down. So to obviously prevent this, marathon runners will eat during a race, and I used energy gels. I took an energy gel roughly every 7 kilometers, which I found worked for me when I was training. And the point of consuming food during a race is to try and offset the energy lost through running, obviously, you know, to provide that glucose to keep you going. Studies have compared eating like a lot at once just before you reach that point of fatigue versus continuous feeding, which is what I did, and even though they both can be effective, the latter, so continual feeding, is generally preferred, because if you eat a lot at once, for example, you are probably gonna cause some digestive issues, some discomfort, a bit of upset down there, and you know, it also means that your body will have to divert more blood to the digestive system so it can digest more of that food, and that means that it is diverted away from the working muscles. So generally consuming little and more often is preferred for most marathon runners. So the last section of this video is going to be all about like hydration, and we're going to talk a bit about hyponatremia, because when I finished the race I felt incredibly dizzy, lightheaded, confused, nauseous, you know. I had to be taken in a wheelchair to the paramedic tent, let's just put it that way, you know. I don't really know what happened to me, but I think my biggest mistake during the marathon was that I was only drinking water during the race. I wasn't consuming any liquid or fluid that contained salt and electrolytes. Hyponatremia, not hypernatremia, basically refers to very low sodium levels, and it's essentially the opposite of dehydration. It can be associated with exercise, and in my case it was because I was consuming just water, and that meant I was flushing out all of the sodium in my body. At the same time I was sweating and losing salt and electrolytes that way, and so that combined with me just drinking water and diluting my sodium, I experienced, I think, mild hyponatremia. Now you can also feel lightheaded after you stop running, because when you are running your muscles are contracting, and that assists the blood flow back to your heart through your veins, which don't contract themselves. They rely on muscle contraction to move the blood through them. So when you're running, you're pumping the blood upwards against gravity back to the heart, and then that can be pumped around the body to other sites, including the brain in particular. And so when you stop running, that doesn't happen as efficiently, and so blood can kind of like collect in your legs. It doesn't really sit there, but you know, it's not moving as efficiently back to the heart through the veins, and so that is another reason why you might start to feel lightheaded when you stop. The final thing to talk about is sweat. As I said, we sweat when we run, and that is because we want to cool our bodies down. In our bodies, we basically have thermoreceptors. We have thermoreceptors in a region of our brain called the hypothalamus, and that monitors the temperature of blood flowing through the hypothalamus. And we also have thermoreceptors in the skin, which kind of monitor the external temperature. But our thermoreceptors, essentially, they will detect when there is a rise in our core body temperature, obviously when we start to exercise. That results in a variety of mechanisms that help to cool our bodies down, one of those being sweating. And the reason why sweating cools you down is because the water that has to evaporate requires heat energy, and that heat energy is derived from our bodies. So if you didn't replace any of that fluid lost through sweat as you're running, that can again cause complications, because if you lose fluid through sweat and you don't replace it, then your blood volume will decrease and your heart has to work harder, i.e. it has to beat faster to pump just as much blood around the body. Because the heart is now working harder, it demands more energy itself, so more oxygen and glucose for respiration. And ultimately it means that less oxygen is delivered to our working muscles. And so that means that we have to start respiring anaerobically. So instead of respiring aerobically with oxygen, we have to start using anaerobic respiratory pathways, which can result in the production of lactic acid, which increases the acidity of our blood in our muscles, and that can compromise muscle contraction as well. So again, you have to be consuming and replacing the fluid lost through sweat in order to prevent this from happening, you know, and to keep our bodies functioning efficiently throughout the marathon. Okay, so that was everything I wanted to cover. I know there has been a lot in this video, but there is so much to talk about. There's so much I didn't even talk about, but I really hope this was an interesting video. You learned something from it. At the end of the day, yes, you put your body under a lot of stress and you have to work really hard, but running a marathon has literally been one of the best things I've done in my whole entire life. So if anything, I hope this video inspired you to maybe consider running a marathon or running a certain endurance event, whether that's cycling, swimming, a triathlon or something, you know. So definitely give this video a thumbs up if you enjoyed it, comment down below and subscribe if you're new. And as always, I will speak to you very soon in another video. Bye guys!